Yeah, here we go. Let us at first consider a kind of high-dimensional data set, right? Which is here simply illustrated as 3D high-dimensional data set. And by projecting the dimensions or the data onto 2 dimensions of the data, then we get a well-known scatter plot, right? So if we consider now all possible plots of an high-dimensional data, then we get a scatterplot matrix. And a very famous term of the scatterplot matrix is actually the term SLOM, which I also like to use within this talk right here. Okay, a SLOM is actually a symmetric matrix of bivariate plots, which means that the entry at position I and G equates to the plot of the dimensions I and G, right? So, and due to the symmetry, a SLOM can be pretty well illustrated either as upper triangular matrix or as lower triangular matrix. Okay, and SLOMs are pretty popular in visual analytics and visualization due to a couple of reasons. So, for example, it's definitely easy to evaluate bivariate correlations, clusters, trends, and so on and so forth. It's definitely easy to implement, right? And it can be very well combined with further interaction techniques, as we have, for example, seen pretty well yesterday in the EuroVis session. And at least for an experienced user, it's able to form hypotheses about multivariate relations based on such a SLOM. So then the question actually is, okay, why not using a SLOM in any analysis situation? And the reason is pretty clear, due to that SLOMs actually scale poorly. So the number of plots which within a SLOM grows quadratically with the number of data dimensions. So, for example, for 10-dimensional data, we get 45 plots. For 33-dimensional data, we get actually hundreds of plots. And for 128 dimensions, we get even thousands of plots. And this scalability issue causes a couple of analysis problems. For example, an intuitive analysis to find relevant plots quickly is for a user actually challenging, definitely time-consuming, and it might at the end overburden the user a bit or a lot. And yeah, therefore the question is, how can we find relevant plots quickly, right? And a couple of approaches exist that address this scalability problem. So, for example, Enquist and colleagues proposed to illustrate all plots along an interactive path within a scatterplot matrix. This way that the context is preserved by kind of a 3D transition. So obviously you can do this, but unfortunately it's definitely time-consuming in order to see all plots over time. Therefore, the quality measures has been introduced a little bit later, and the quality measure measures the relevance of a plot with respect to a certain feature in it. So this means the quality measure maps a feature onto a real number. That's it. So for example, the ratio of maximum and minimum stretch in a plot can be considered as a measure of correlation. And then a very simple approach to apply quality measures is thresholding. And this way we get all plots that potentially show correlation in the data. It's pretty nice. But unfortunately, these plots are spread over the entire score. So they are not covariant to each other. They cannot be really well compared with each other. This is a problem. And the number of plots is not steerable with this approach, which can be a problem for the user. Another very famous approach is the graph theoretic diagnostics from Wilkins and colleagues. And here the idea is, okay, we measure the relevance of a plot with a lot of quality measures. And then we illustrate the quality measure values within a diagnostic form of quality measure values. And at the end, we get a diagnostic plot which has a constant size. So it means it's independent of the dimensionality of the original plot, which is pretty well. But unfortunately, this kind of approach is, for at least one inexperienced user, definitely hard to interpret due to this very high level of abstraction. To overcome this issue, a couple of reordering approaches has been introduced. And here reordering means, okay, we reorder the dimension this way, that we separate relevant plots from non-relevant plots. This is the idea here. But unfortunately, reordering means to find an appropriate permutation of the original splom. And this permutation issue is NP hard. So reordering just works well for rather small sploms. To overcome this issue, yet a couple of heuristical reordering approaches exist. For example, Arikirki and colleagues introduced an information-aware heuristical reordering approach. And here the idea is, okay, we measure the mean value for all quality measures over a certain dimension. And then we do it for all dimensions, and then we reorder the metrics with respect to these mean values. And what we finally get is a kind of a splom where the relevant plots are pretty well separated from the non-relevant ones. So this works well. But unfortunately, this approach only works as long as the variance of the quality measures within a dimension is rather low. Okay. So by considering now all those related works, we can see there are a lot of advantages and a lot of disadvantages in order to select relevant plots from a large splom or a splom in general. And in order to systematicize the requirements a bit, we introduce some selection criteria which are derived from the related work and which need to be fulfilled by an appropriate selection approach. And the first is, okay, an explorative analysis should be enabled. Pretty well. We don't want an analysis for which we need a priori knot. This is the idea here. The second is the plots should be coherent. It has to be able that the plots can be mutual compared to each other. Of course, the approach should scale. This is actually the reason why I'm here. The number of plots should be also steerable, because the user has to decide how many plots he or she wants to get. And also the relevance of plots has to be steerable actually due to similar reasons. And therefore we introduce a kind of a greedy approach to select large amounts of plots which are coherent from a scatterplot matrix that actually fulfill these criteria. And for this, we measure at first the relevance of the plot. So this means we apply a quality measure to it, which is here colorized for reasons of illustration. So red is, for example, a very relevant plot, and green is a rather non-relevant plot. Okay, and then we reorder the dimensions to separate relevant from non-relevant plots. And for this, we apply a local square difference measure locally to the splom and sum this up over the entire splom. And then we get, for example, here a value of 72 point something. And we are looking now for this pair of dimensions which need to be swapped in order to reduce this value best, which is the 2 and the 4 in this example. And then we continue, or this optimal swapping of dimensions is actually continued until this heuristical reordering converges in a local minimum at 27 point something. And then we get also a splom which separates pretty well the relevant plots from the non-relevant plots. This is pretty nice. But this approach does not have the disadvantages that the formerly mentioned mean value approach has. So here also the variance within the dimensions with respect to the quality measures can be also large. It works nevertheless. Okay, so then the question occurs, is this local square difference measure actually reasonable? And to figure this out, we did an experiment with 900 random sploms for the dimensions 50, 70, and 150, and for the measures local square difference measure, local standard deviation, and local min-max differences. Okay, and then we can define the improvement as define the reorder runtime as Yes, the computational time while the reordering process. And then we can take some statistics and we can see, oh, okay, for both the improvement as well as the reorder runtime, the local square difference measure works pretty well and is better than the other measures, and therefore we skip them. Okay, and if we take a look to very large number of dimensions, we can see that this local square difference measure in combination with this heuristical reordering causes clusters of relevant plots within our scatterplot matrix or within our reordered version of the scatterplot matrix. This is what we want, actually, but nevertheless, this reordered plot is not really ready for application yet due to, I need to refer to abstractions, especially due to the reason that the human perception system, so actually the user, we, is subjected to a couple of optical illusions. So for example, the strobe effect, after images, shutter effect, and simultaneous contrast. So for example, the strobe effect means the more stimuli are present to a user, the worse he or she is able to conduct a certain interaction task. This can be a problem. And an after image means if you change the view from one part of this plot to another part, then a virtual image occurs. And shutter effect and simultaneous contrast means that neighbored textures and colors mutually influence their perception. And we have to overcome these problems to give the user an appropriate tool, actually, and to reduce this effect, we at first apply a low-pass filter, just in order to remove outliers. And then we apply a histogram equalization in order to redesign the histogram this way that the visual contrast is maximized. And finally, we quantize the values to 7 value steps, which are then mapped onto an appropriate color map. And for this we use here the sequential or diverging color map from the color Pur, which is very famous, based on Harrower and Pur from 2003. And this gives us actually the abstracted version of the reordered plot, right? And this is named ACE plot, and it uses optical illusions and makes this way an interaction more feasible with a reordered plot. And some interaction approaches can be used now in order to select clusters of relevant plots within such a kind of an ACE plot. So for example, where we really want is the option to use a circle metaphor with a variable radius. This makes sense due to that the clusters have often very curvy boundaries. And then an alternative is also given by exploiting the fact that the clusters are bounded by a constant color. So we can of course use a very simple plotful based approach in order to select those clusters. Okay, and then with an interactive tool, we can use the interaction approaches to select clusters of relevant and covariant plots as a kind of a visual lens, right? So for example, we see here the exploration of the communities dataset that has 128 dimensions and more than 8,000 plots. Okay, and of course we are now able to extend this kind of approach. I mean, we have here just one ACE plot. We can also use a couple of ACE plots at once in order to provide more analysis properties to the user, and then it's possible. I mean, the ACE plot each ACE plot is based on a different quality measure, right? And then we can select an area within an ACE plot and also the related area, and all the other ACE plots is emphasized in order to get a kind of linking and brushing between them and to figure out some hidden relations is possible. Okay. So finally, our tool also provides user-specific, it is possibilities. For example, you can choose and change the color map scheme. Maybe you like other color maps more, then it's definitely with our tool. So, in order to figure out whether this approach is really usability, or has a good visibility or not, maybe not, I never know. We got some user feedback, and we asked therefore very low number, 12 participants of the age 22 to 30 years to select as many plots as possible with high relevance or large relevance. Especially for a couple of ACE plots from the communities dataset and from the census dataset. And here of interest were actually the ACE plots with diverging column map, the ACE plot with sequential column map, the reordered plot, and the original plot, of course, color. So then here we have some results for the communities dataset. I mean, the results for the census dataset looks quite similar. And now important is how relevant were the plots in average that were selected, and how many plots were selected in average. And then we can see, okay, the ratio for the abstracted plot, for the ACE plot, is by far the best with respect to the performance of reordered plot. And let us go a little deeper into the evaluation results, here led by the wedge test, and then we can see, okay, the abstraction process as well as the reordering process seems to be reasonable, because it reveals significantly better results than the original SLOM would reveal. This is pretty nice. Nevertheless, a significant difference between using a sequential column map or a diverging column map cannot be revealed for the time being. Okay, this result is pretty nice, but please note that it just shows a trend of our concept due to the really low number of participants. So it means to confirm this result in the future, we need more studies with more data set and more participants. So, but we have a good feeling about it. Okay, so let me actually conclude this talk. We presented an approach of selecting large amounts of plots from a large scatterplot matrix, so which has a large number of dimensions. And it's pretty nice because it implements the Snyderman mantra. Overview first, zoom in and filter, then details on demand. It satisfies the formally mentioned selection criteria. And it's, at least from our point of view, simple to use for also for unexperienced users, right? Nevertheless, there are also some limitations. It's definitely a greedy approach, so we get just a local minimum while the reordering, and this can be a problem. And of course, the plots themselves that we get for the exploration are coherent. Okay, this works pretty well. But the clusters of plots are not coherent. So this means we just look at one combination while the reordering, not at all combination. Maybe we overlook something. It can be, we can never know. And therefore we have a lot of work to do in the future, or some couple of work. We should definitely improve the reordering with more heuristics and measures. As I said, we need more studies, more participants, and more data sets. And also, we should include some more interaction techniques in this prototype in order to further improve this technique. Okay, so far that's it. I hope you like this approach a bit. I hope really. And nevertheless, thank you for your attention. I'm open for your questions. Thank you.
Okay, so please ask questions and say if you don't like this approach. Marschnicker from the University of Marburg. I like the approach a lot. And what you pointed out is the importance of the reordering. And you know that, may know that reordering is an important problem in bioinformatics. So there are a couple of packages, for example, in R. So you may go for seriation package, or computational methods for business analytics, or something else. These packages are specifically designed to reorder swarm matrices. And it goes from hierarchical clustering plus optimum deep ordering, or with like simulated annealing, and with many other methods. because finally what you do is the manual reduction of a very complex matrix to a linear reordering. So it's just have a look.
No, thank you for the comment. I know a lot of different methods. The problem is if you assume that you do not have application knowledge, and this is what we assume. I mean, if you have application knowledge, there are methods that work for a couple of cases better than others. But if you assume you do not have application knowledge, and this is our point of view, then it's difficult to find a measure that works in any cases. But I don't want really give this idea, or I don't want this idea to only make explorative analysis available here for this kind of approach. But you're right, I know a couple of them, and I also tested a couple of them. But it depends on the data. If you change the domain, you know, the domain properties, then some measures work better than others, of course, and also some reordering approaches. But this is also a question of time. This works pretty well because it's just a complexity of a square complexity. Maybe in the leading is better, but maybe slowly in this case, and you never know. There's a problem here. We have a decision problem at the end of the day. Right. Thank you for coming.
More questions, please? No questions. I had one. So at the end of your paper, you wrote that you would like to add more civilizations. I'm not perfectly sure what you mean with that. So have you any specific things in your mind?
Yes and no. I mean, if you have a visualization technique that is able to be integrated in such a kind of a metric scheme, you can, and you have a quality measure for it. I mean, a lot of quality measure exists for parallel coordinates, for example. Then you can also use or extend this approach one-to-one to the new visualization technique. And there is, for example, a technique for parallel coordinates metrics published a couple of years ago at the DMV. And for those kinds of visualization metrics, this approach can also be applied. Of course, sure. It's a very obvious extension.
Yeah, thank you. We would have time for one more question. No, obviously not. Then I will close the session now. Thank you very much, and thank you for all.